So, hello students, good evening. So, today we are going to see the thermochemistry part of the thermodynamics lesson. Okay, in the last session we have discussed the thermodynamics part, and today we will discuss the thermochemistry. Okay, as a crash course. And coming to the point, so the topics that we are going to cover today are the thermochemical equation, Tesla, thermochemistry, spontaneity, Gibbs free energy, and Gibbs free energy with equilibrium constant. So I will give you the formulas that are related to these topics, and then we will solve the previous year's questions of JEE and NEET on this 5 topics. Okay. So starting from the thermochemical equation, the first is the enthalpy of reaction. So what is enthalpy of reaction? It is the energy change accompanying a reaction is enthalpy of reaction. Okay, so there is a reactant giving product, and if I want to find out the delta HR, which is the enthalpy of reaction, then I have to do the sum of the enthalpy of product minus sum of the enthalpies of reactants. Okay, or I can write like this also, summation of the enthalpy of the product minus the summation of the enthalpies of reactants. Okay, so this is the formula, very important formula you have to keep in mind. Then coming to the next point, standard enthalpy of reaction. So it is the enthalpy change for a reaction when all the substances are in standard state, and it is denoted by delta HR naught. Okay, it is delta HR naught. Standard temperature means 298 Kelvin and standard pressure is 1 bar pressure. Got it? So I'll give you some standard form of some elements. And for carbon, the standard state is graphite. And for bromine, it is liquid. And for oxygen gas, iodine solid, nitrogen gas, red phosphorus is also a solid. We have white phosphorus, red phosphorus, black phosphorus, right? And among that, red phosphorus is the standard form of the phosphorus. And about mercury, liquid form is the standard form. And coming to the sulfur, rhombic sulfur is the standard state of sulfur. Okay. So these are the standard state of some of the elements. If 1 mole of the compound is formed from any of its standard state, then we call that as the enthalpy change accompanying that particular process is called as standard enthalpy of formation. Okay. And some more examples for you. Now here you see calcium oxide is reacting with carbon dioxide to give calcium carbonate. Okay. And here delta HR naught is given. But it is not the standard enthalpy of formation. It is a standard enthalpy of reaction. Why it is not called as standard enthalpy of formation? Because we have calcium, carbon, and oxygen here. Okay. The standard state of calcium is calcium in solid form, but it is present in calcium oxide form, not in the form of calcium. The constituent element is calcium. And for carbon, graphite form. For oxygen, it is O2. But here we don't have such elements. We have calcium oxide and carbon dioxide. So, CaCO3 is not formed from its constituent elements, but it is being formed from some other compounds. So, delta HF naught, that is standard enthalpy of formation, cannot be written for this reaction. Okay. In the same way, here you see for hydrogen reacting with bromine giving HBr, 2 moles of HBr is formed. The definition says that only 1 mole of the compound should be formed from its constituent element. Here hydrogen and bromine are constituent element only for hydrogen HBr, but 2 mole is being formed. So delta HF naught cannot be written. Okay. Yes, coming to the next topic, Hess law. So what is that? It states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So we have A is giving B, the enthalpy change accompanying that reaction is delta H. And we can go to A to B in many steps also. So if I add all these steps, it will be equal to the delta H. Okay, delta H is equal to delta H1 plus delta H2 plus delta H3. So this is Hess law. Got it? Now coming to the thermochemistry, The first term is standard enthalpy of combustion. It is denoted by delta H naught C. It is enthalpy change when 1 mole of the substance is completely burnt in presence of enough sufficient supply of oxygen. For this, all the reactant and product should be in their standard state. Pressure should be 1 atmospheric pressure and temperature should be 298 Kelvin. Okay, and here you see butane is burned with 6.5 moles of oxygen, producing carbon dioxide and water. And we can write the standard enthalpy of combustion for this reaction. It is around minus 2658 kilojoule per mole. Okay, and the next term is standard enthalpy of atomization. When 1 mole of any substance is converted into its gaseous individual atoms, we call that as enthalpy of atomization. Okay, product should be in gaseous state for this, and it is an energy absorbing process, so it is endothermic. So here you see an example is given. Hydrogen, we have hydrogen molecule, and if I give energy, hydrogen molecule will be converted into its gaseous atoms. Okay, it is getting converted to atom, so that's why it is called as atomization. Energy absorbing, no, so delta H value will be positive, so that's why here the value is positive. And sodium in solid form, it is getting converted into its gaseous atom, and here in this, for this particular reaction, atomization enthalpy is equal to sublimation enthalpy. Solid getting converted to gases, sublimation, no, so here both are same. Okay, coming to the next term, bond enthalpy, denoted by delta H naught bond enthalpy. So it is energy absorbed in breaking 1 mole bond in gaseous phase. So I have a molecule, chlorine molecule here, and it is in gaseous phase. I have to break this bond. Okay, so 1 mole of this gaseous molecule is broken down to form the corresponding gaseous atom. The energy required to break this bond is called as bond enthalpy, and it is 242 kilojoule per mole. It is positive. You see, the value is positive. Bond breaking is always positive. Okay, all the reactants and products must be in gaseous state. In the previous case, only products should be in gaseous state, but here both reactant and product should be in gaseous phase. Okay. Now coming to the next thing, enthalpy of reaction in terms of bond energy. So for this reaction, methane reacting with chlorine to give CCl4 and HCl, we have A plus B giving C plus D. Okay, delta HR naught from bond enthalpies can be calculated from this formula. Bond enthalpy of reactant minus summation of bond enthalpy of product. If you want to calculate the bond, the change in the enthalpy of reaction, standard enthalpy of reaction from bond enthalpy, do reactant minus product. Reactant minus product. And here the substance should be in gaseous form. And here HCl, you see, it is not in gaseous state. So you have to consider only these three. Okay, reactant minus product. Now the next topic, lattice energy and hydration enthalpy. What is lattice energy? Energy required to break 1 mole of ionic compound in solid state to form free gaseous ion is called as lattice energy. So 1 mole of sodium chloride is taken, okay, and it is broken down so that Na plus and Cl minus is coming out, okay, and in the form of gaseous, free gaseous ion, and the energy that is required to break this 1 mole of the compound is called as lattice energy. Okay, so it is positive. Bond is getting breaking, no, bond breaking process, so it is always endothermic, so delta H value will be positive. For the energy absorbed and the energy released process, in case of absorbed, when the energy is getting absorbed, 1 mole will give its constituent ions, and here gaseous ion will give 1 mole of the ionic compound. And in case if the energy is absorbed, bond breaking occurs, and if the energy is released, bond formation occurs. You can see the example here. And for energy, if energy is getting absorbed, delta H is positive. If energy is released, process is exothermic, so the delta H will be negative. Okay. Now coming to the hydration enthalpy, delta H naught hydration, it is the enthalpy change when 1 mole of a substance or ion is completely hydrated by water. You see here, I have taken 1 mole of the sodium ion. It is forming the bond with the water molecule. These are the water molecule. Water is polar, right? It is a polar solvent. So it is forming bond with the water molecule. It is taking enough water molecule, and all the water molecules negative end, that is oxygen end of each water molecule, is surrounded. Okay, negative end of the water molecule is surrounding the sodium plus cation. This is called as the hydrated ion, and here bond formation is occurring between the cation and the water molecule. Bond formation means it is exothermic, right? So that's why delta H is negative. When 1 mole of the substance or ion is completely hydrated by water, then the energy that is getting released from that bond formation process is called as hydration enthalpy. Okay. Coming to the enthalpy of solution, enthalpy of solution can be calculated by adding the lattice enthalpy and hydration enthalpy. Okay, and the solubility of ionic compound decreases with increase in lattice enthalpy and increases with increase in hydration enthalpy. Okay, they are inversely proportional to each other. Coming to entropy versus spontaneity. So what is a spontaneous process which does not need any help of an external agency is called as spontaneous process. So in both the cases you see, so when I bring this hotter object A to the colder object B, the heat will automatically transfer from A to B, right? Heat will automatically flows from hotter object to colder object. So I don't have to do anything. I'm just bringing them together and keeping them together. That's all. So it is automatically, without any external agency, the process is occurring. So those processes are called as spontaneous process. And here in the second example, you see water flows down the hill. Water is coming from top. I'm not doing anything. It is just automatically coming. So it is a spontaneous process. It cannot be reversed. Spontaneous process cannot be reversed without the help of external agency. If I'm not doing it to reverse it back, it will not go back to its original position. So those types of reactions are called as spontaneous reaction. Okay. And every system tries to reduce its energy in order to gain the stability, because energy and stability are inversely proportional to each other. The system will always try to keep them at its lowest energy because it can attain the stability at its lowest energy point. Okay. Now coming to the entropy, which is denoted by the letter S. Entropy is otherwise called as the measure of degree of disorderness or randomness. Very important. The measure of degree of disorderness or randomness in a system is called as entropy. Okay. So here you see, let me keep this as solid, and this is liquid, and this is gas. In case of solid, regular arrangement of atoms will be there. So it is more ordered. So the entropy of a solid is very less. If the randomness is more, entropy is more. Because randomness is nothing but the entropy. They are directly proportional. Randomness is directly proportional to entropy. Okay. In case of liquid, the arrangement is little bit less. So entropy will also be kind of what to say, it will be more. Okay. And here less ordered because randomness is more. Everything is randomly arranged. Means the entropy is also more. So the entropy of a gas is more than liquid than solid. Okay. And let's see some more points about entropy. First of all, it is a state function. Okay. And depends only on the initial and final state of the system. It is an extensive property in which it depends on the mass of the substance or the amount of the substance. If I change the amount, entropy also differs. And the change in entropy of a gas is more than liquid than solid. And if I want to find out the change in entropy of a reaction, do product minus reactant. Change in summation of change in entropy of product minus summation of change in entropy of the reactant. Okay. And entropy can be represented in terms of enthalpy or heat or in terms of temperature. Okay. So both will give this. Delta S is equal to Q by T. Heat exchange in the reversible process by temperature. If I change this delta S to small s, okay, I will get ds equal to dq by T. And the total entropy change, that is delta S of universe, will be equal to the sum of the entropy of system and surrounding. Okay, so entropy of the system and change in entropy of the surrounding will give me the change in entropy of the whole universe. Got it? Now coming to the entropy versus spontaneity, which is otherwise called as the second law of thermodynamics. So I am taking gas A and gas B and mixing both the gases together. Now in this mixture, the randomness of A and B increases because the volume is more, the space is more. So the gas molecules can move randomly, more randomly. Okay, so this states the second law of thermodynamics, in which the entropy of the universe is increasing. Entropy, this is universe, and this is B. Okay, so randomness increases for the universe, so the entropy also increases. So entropy of the universe will be greater than 0 according to second law of thermodynamics. Okay, so it leads to this equation, system plus surrounding giving universe. And for different entropy for different process. Good evening, Pooja. Good evening. So I am discussing thermochemistry part. Okay, once I'll finish this theory part, I will go with the problems. Now I am doing with spontaneity. Right? Now the entropy for different process, we have two different process. One is reversible and the other one is irreversible. For reversible process, delta S is equal to 0. But for irreversible, it is greater than 0. Okay, just to keep in mind, these points are very important. Now coming to the next topic, Gibbs free energy. It is denoted by the letter G, and we have some more important points to be kept in mind about this. The first point is, it is also a property of a system. Okay, it is a state function in which it depends only on the initial and final state of the system, and it is also an extensive property like entropy. Property means the value changes on changing the size of the system. And also it has one formula, G is equal to H minus Ts, and delta G naught is equal to summation of delta G naught of product minus summation of delta G naught of reactant. Okay, here product minus reactant. So all these points you keep in mind. Now, G cannot be measured. Only delta G can be measured. So delta G is equal to delta H minus T delta S. Very important formula. Delta G is equal to delta H minus T delta S. And for spontaneous process, delta G will always be 0. Means it is always negative. Only if delta G value is negative, the process will be spontaneous. If it is equal to 0, equilibrium. If it is greater than 0, it is non-spontaneous. Okay. If it is positive, it is non-spontaneous. So for a spontaneous process, delta G value should be always equal to, that is, it should always be less than 0, that is negative. Okay. And one more important tabular column I'm going to give you. So this is that one. For non-spontaneous, delta G is going to be positive, and here you can find the sign notation. And for spontaneous, it will always be negative. And at low temperature, it is spontaneous. At low temperature, it is spontaneous. And here for high temperature, it is spontaneous. And the signs of the other delta H and delta S, you can note it from here. Okay. This tabular column is very, very important. Now coming to the last relation, which relates Gibbs free energy and equilibrium constant. If I'm having A reactant and it is giving B and both are in equilibrium with each other, if I want to write the delta GR for that, I can write like this, where Q denotes a reaction quotient. It is product by reactant raised to their stoichiometric coefficient. At equilibrium, this part is going to be 0 and Q will be equal to KEQ, equilibrium constant. So if I replace that, I will get this equation. And if I want to convert ln to log, what I have to do? I have to multiply by the number 2.303 so that I will get log. So minus delta GR naught is equal to minus 2.303 into RT into log of KEQ. Okay. So this is one of the very important formula which we will use to find out the equilibrium constant using delta GR naught. Okay. Now using all the formulas that we have seen now, we will try to solve the previous year's questions of JE and NEET. Okay. Let's start from the first. Consider the following reaction: 2H2 plus O2 giving 2H2O, and delta HR naught associated with it is minus 483.64 kilojoule. What is the enthalpy change for decomposition of 1 mole of water? So what I have to do? First, I have to reverse this equation, right? Because water is getting decomposed. So 2H2O giving 2H2 plus O2. So since I have reversed this equation, I have to change the sign of delta HR naught. It will be equal to, it is given in minus, so it is plus 483.64 kilojoule. Okay. Now I have to calculate for only 1 mole of water. Here it is given for 2 mole. So what I have to do? Divide this equation by 2. So this will give me H2O giving H2 plus half wood. What I have to do? I have to divide this delta HR naught by 2. So if I divide this by 2, I will get plus 241.82 kilojoule as the final value for delta HR naught. Enthalpy change. Okay. So option B is the correct answer for this question. Now coming to the next question. The equilibrium concentration of the species in the reaction A plus B giving C plus D are 2, 3, 10 and 6 mole per liter respectively at 300 Kelvin. Delta G naught for the reaction is, and R value is given in terms of calorie per mole Kelvin. So it is 2. What we have to do? Take the relation which relates delta G naught and equilibrium constant. Just now we have seen, right? It is 2.303 into RT into log of KEQ. Okay. So it is equal to minus 2.303. R value is 2 and the temperature is given as 300 Kelvin. 300 into log. So how to write the equilibrium constant? It is the product concentration divided by reactants concentration, right? So the product C and D, they have 10 and 6. So it is 10 into 6 divided by 2 into 3. So just simplify this. So we are getting log 10. Log 10 is equal to 1. So 600 into 2.303 into 600 we are having. So it is equal to minus the 1381.80 calorie. Delta G naught is equal to minus 1381. Okay, so option B is the correct answer for this question. Okay. Now coming to the next question. For irreversible expansion of an ideal gas under isothermal condition, the correct option is isothermal means the temperature is going to be constant. Okay. If the temperature is constant, then delta T is equal to 0. And it says that it is irreversible expansion. Irreversible process is always spontaneous. Irreversible processes are always spontaneous. If the process is all normally for spontaneous process, delta S of the universe will be greater than 0, right? And irreversible is always spontaneous. So here the delta S value is going to be greater than 0. Means it is not equal to 0. Okay. And also it says that temperature is constant. So we know that delta U is equal to NCV delta T. So delta T goes to 0. So delta U is also equal to 0. Okay. So delta U is 0. Delta S is not equal to 0. So option D is the correct answer for this question. Okay. Fine. Moving on to one more thing. Hydrolysis of sucrose is given by the following reaction. When sucrose reacts with water, it gives glucose and fructose. If the equilibrium constant Kc is 2 into 10 to the power 13 at 800 Kelvin, the value of delta Gr naught at the same temperature will be. So now, how to find out? We have to take that relation back again. So delta Gr naught is equal to minus RT into ln Keq, right? So it is equal to, and R value is 8.314 joule per mole per Kelvin into the temperature. It is not 800, it is actually 300. So it is 300 Kelvin into ln equilibrium constant Kc or Keq. It is 2 into 10 to the power 13. Okay. So this is your delta Gr naught value. So where it is given? It is given in option D. So option D is the correct answer. Okay. Fine. Moving on to the next question. For the reaction 2 chlorine, just give me a second. So for a reaction 2Cl giving Cl2, the correct option is, okay. So here 2 chlorine atom is getting converted to chlorine molecule. Yeah, chlorine molecule. So here you see it is a bond formation process. 2 chlorine atoms are getting uh, combining with each other and it is forming a bond. So bond formation occurs. Bond formation occurs. So bond formation is an exothermic process. Bond formation is an exothermic process. And if the process is exothermic, then delta H value is negative. Okay, means delta H is less than 0. Delta H is less than 0. So option B or option C should be the correct answer. Now, 2 chlorine atom is getting converted to 1 chlorine molecule. So 2 chlorine atom is getting converted to 1. So here the number of particles decreases. Number of particles decreases. If the number of particles decreases, so the entropy should always decrease, means the delta S value should be less than 0. Delta S is less than 0. Okay, so option C is the correct answer for this. Okay, now moving on to one more thing, in which case change in entropy is negative. So in case A, sublimation of solid to gas. Solid is getting converted to gas. So we know that entropy of a gas is more. Okay, entropy of a gas is more and entropy of a solid is less. So change in entropy is also less for solid and more for gas. So if entropy is more, the value will be positive, right? So it is not negative, it is positive, and here only it is negative. And coming to two hydrogen giving one hydrogen molecule, here 2 particles getting converted to 1. Okay, so the number of particles decreases. Number of particles decreases. So entropy will also decrease and change in entropy will be negative. So option B is the correct answer. In evaporation of water, liquid water will be converted to gaseous water. And here also entropy is increasing, so it will be positive. Expansion of a gas at temperature. During expansion also, in a container, if expansion occurs, so they will try to move very far away, randomness increases. So entropy also increases and it will be positive. And only in second case, entropy is negative. Okay, because it is a bond formation process also. For all the bond formation process, entropy will be negative, right? So in that way also we can study this question. Coming to the next question, for a given reaction, delta H is given as 35.5 kilojoule per mole, delta S is given as 83.6 joule per Kelvin per mole. The reaction is spontaneous at. Okay. So for the spontaneous reaction, for a spontaneous reaction, we know that delta G should be less than 0, right? That is, delta G is equal to delta H minus T delta S. This value should be less than 0. So what is T? T is delta H by S, right? By delta S. So and T should be greater than delta H is 35.5 kilojoule. 35.5 kilojoule. Kilojoule means 10 to the power 3. It is 1000 divided by delta S is 83.6. So it is equal to 424.6, which is approximately equal to 425 Kelvin. So the temperature is greater than 425 Kelvin. So option A is the correct answer. Option A is the correct answer. Okay. Just use this relation. Delta G is equal to delta H minus T delta S relation you use to get the answer for this question. Okay, which is very important relation. Now moving on to one more question. A2 plus B2 giving 2AB. For this reaction, the standard enthalpy of formation is given as minus 200 kilojoule per mole. Okay, and here AB, A2, B2 are diatomic molecule. Yes, 2 atoms are there, so they are diatomic. If the bond enthalpies of A2, B2 and AB are in the ratio 1 is to 0.5 is to 1, then the bond enthalpy of A2 is. So how to find out? So let the bond enthalpy, let the bond enthalpies of all these three be x, 0.5x and x. Okay. So to find out the delta HF naught, it should be equal to the summation of bond energy of the reactants minus the summation of bond energy of the products. Right. So delta HF is given minus 200. For the reactant, who is a reactant A2 and B2? A2, B2 are in the ratio x and 0.5x minus product is x. Product is x, but we have 2AB. So it is 2x. So x plus 0.5x is 1.5x minus 2x. It is equal to minus 200. So minus 200 is equal to minus 0.5x. So minus minus gets cancelled. So x will be equal to 200 by 0.5. It is equal to 400. So x is equal to 400. So the bond enthalpy of A2 is 400. Okay. Now coming to the next question. For complete combustion of ethene, the amount of heat produced as measured in bomb calorimeter is 1406 kilojoule per mole. Heat is produced. So it should be negative. Okay. And the temperature is 300 Kelvin. The minimum value of T delta S needed to reach equilibrium is minus dash kilojoule. R value is given as 8.3 joule per Kelvin per mole. So to find out the T delta S value, we need delta H. And how to find out delta H? Delta H is equal to delta U plus delta Ng RT. So delta U, the amount of heat produced is given. So it is minus 1406 plus delta Ng. It is nothing but the number of moles of gaseous product minus number of moles of gaseous reactant, right? So gaseous product is only carbon dioxide and the number of mole of carbon dioxide is 2. And the gaseous reactants are 1 ethene and 3 O2. So it is 4. 1 plus 3 is 4. So the answer is minus 2. Minus 2, R value is 8.3 and the temperature is given as 8.3 joule per Kelvin. But we have to find it in kilojoule, right? So we can multiply this by 10 power minus 3 into temperature is 300. Now here it is minus 1406 minus 4.98. So the delta H is coming out to be approximately minus 1411 kilojoule per mole. Okay. Now at equilibrium, we know that delta G is equal to 0. So delta G is equal to delta H minus T delta S, right? So delta G goes to 0. So delta H minus delta T delta S is 0. So delta H is equal to T delta S. So we know delta H. So it is equal to T delta S. So in the question we have to find out T delta S. That is equal to minus 1411 kilojoule. Minus 1411 kilojoule. Okay. Coming to one more question. The value of log K for the reaction A giving B at 298 Kelvin is delta H naught is given, delta S naught is given. Okay, everything is given. We have to find out log K. Now, using the given values, we can use delta G naught equal to delta H naught minus T delta S naught relation. So using this, we can find out delta G, and from delta G, we can get log K. Okay. So what is delta H? Minus 54 kilojoule. But we have to represent in terms of joule. So convert this to kilojoule, multiply by 10 power 3. So it will give you 54070 minus temperature is 298 Kelvin, no? So 298 Kelvin into delta S naught. Delta S naught is 10. Delta S naught is 10. So just substitute everything, and here we will get minus 54070 minus 2980, which is equal to minus 57050 joule per mole delta G naught value. And we know that delta G naught is equal to minus 2.303 into RT into log K, right? So we have to find out log K. R value is there, temperature is there, delta G naught is also there. So substitute everything and you will get log K as 57. So minus if you substitute the value of delta G naught here, there we will have minus 57050. So minus will get cancelled. So 57050 divided by R value is 2.303 into 8.314 into 298 to 298. Okay, so this will give us log value approximately 10. We can take whole term as 5705. If we substitute 5705 instead of this, so we will get 10, right? So the value will be 10. So log K is 10. That is the nearest integer. Okay. So coming to the last question for this session, enthalpies of formation of CCl4H2O, carbon dioxide and HCl are given. The magnitude of enthalpy of the reaction given below is. Such a straightforward question, right? Enthalpy, so formation delta HF naught is given. We have to find out the enthalpy of reaction. That is delta H R naught we have to find. It is equal to summation of delta HF of product minus summation of delta HF of reactant, right? Straightforward formula. So now all the reactants and products are in gaseous phase. Just straight away substitute everything. Products are carbon dioxide and HCl. So the carbon dioxide is minus 394 and we have 4 HCl. The value of HCl is minus 92. So multiply this by 4. So 4 into 92 minus, for reactant for CCl4 it is minus 105. Okay, and for H2O, 2 H2O are there. So plus 2 into minus 242. Okay. So now when we do the calculation, minus 394, it will be minus 368, minus into minus plus, so 105. And here we will have plus 484. Okay. Now on doing the calculation, we will get minus 173 kilojoule per mole as the enthalpy of the reaction. Okay. So the answer is minus 173 kilojoule per mole. Okay. So this is how we have to find out. Just we need to apply the straightforward relation to solve this. That's it. Very easy. It is a JE question. That's why we don't have options here. Okay. So I hope the session is very useful and it is very clear to all. Students, those who have joined late, you can go through the thing from the YouTube. Okay. And you can utilize this as a revision of thermochemistry for your exam. Okay. So if you're having any doubt, you can let me know now. There is no doubt. We can meet up with a new lesson tomorrow. Till then, take care. Thank you so much for listening. Bye-bye.